Hi, my name is Zvonimir Bendik, and I work as a senior director in Western Digital Corporation Research, managing the Next-Gen Platforms Technologies Department. Our focus is a new hardware technologies for Western Digital. On the development side, these are the RISC-V embedded processor cores, RISC-V firmware toolchain. And on the more research side, these are machine learning accelerators, as well as new smart networking technologies such as OmniExtend, um, controllers for very low latency memories, and neuromorphic computing. So today at Flash Memory Summit, I will be presenting our open source RISC-V processors for storage controllers. So the agenda for the presentation is introduction to storage controller SoC devices, explanation of the typical flash controller implementations, requirements for the embedded CPU cores, and then our RISC-V Swerve core roadmap. And we'll go through use cases such as acceleration of legacy code, software and firmware toolchain support, multi-threading and IPC improvements, ultra-low interrupt latency, and our small EL2 cores targeting hardware accelerators. So typical storage controller SoC device, what it needs to do is to provide a familiar SATA, SAS, or NVM Express interface to the host and actually manage the persistent media present in a device. A NAND, but it could also be magnetic media or some of the new media such as phase change memory or MRAM. The requirements on the controller are in any particular order: reliability, because obviously storage customer expects no loss of data and expects high reliability of storing the files. Security, such as boot firmware security features that guarantee that firmware is not compromised, and data at rest protection, which encrypts data in real time. Performance, in case of SSDs, consumers expect high IOPS, high data rates. And finally, power, because shift to mobile devices requires saving or shaving every watt. And same as in the data center, there's no difference. So typical flash controller implementation will have a hardware that connects to the host, which can be SATA, SAS, or NVM Express logical protocol that operates on a PCI Express physical layer. It will have a main CPU complex that will run main firmware, communicate with the host, receive the read and write IO commands, and then it will have a datapad, a CPU that manages datapad complex, which in case of this SSD devices needs to manage individual NAND channels. So you will have, depending on a class of device, 2, 4, 8, or even more channels behind which you will have a NAND devices, and each channel will need to have a dedicated IP that will generate the sequencing. That's another opportunity for the embedded core. And the datapad CPU will also have to manage the encryption engine, meaning when it's writing data to the channels, it will have to add ECC code. When it's reading, it will verify ECC code and, if necessary, correct the errors before it communicates error-free data to main CPU. And then main CPU talks to the host and delivers a proper NVM Express formatted data back to the host file system. There is also a root of trust and encryption management, another opportunity for the core. This will verify firmware authenticity on the boot. And it will also manage user credentials for security, and it will only unwrap encryption keys used for real-time encryption if user provides a correct credential, for example, with the TCG security protocol. And finally, there will be a power management CPU that will manage power consumption. So what are then the CPU core requirements? On the main CPU and data path CPU on the upper part of this diagram, these are high performance, typically evaluated on Drystone, CoreMark, or MBench benchmark. And this is important because you want to run legacy code at a higher performance. You had your previous core, you had certain performance level. If you're upgrading the hardware, the expectations are that power will not go up, but you'll be able to run it faster. Low power consumption is always the key. Scalability is very important if you want to actually have schemes to bring more cores, for example, with cache coherence. Software toolchain support is of extreme importance, especially when you're transitioning to new architecture like RISC-V, from where developers do not want any disruption. They want to continue coding in C++ or any other higher level language that's typical for the platform. For flash controllers, it's mostly C, C++. And finally, interrupt latency, very important. These are real-time systems. If there's an interrupt assertion, you want to react in a nanosecond. For auxiliary cores, requirements are low power, even more important because these small cores are often used to implement finite state machines that do a variety of services and hardware acceleration to a main processor. So they're often replicated, multiple dozens of times. So every milliwatt saved is of utmost importance. Efficiency in instructions per clock cycle, you want that to be as close to 1 as possible. And finally, performance is still very important. This is the RISC-V cores roadmap. These cores are available with their source code in the organization called CHIPS Alliance that has many members in our industry and many important companies such as Google, Alibaba, Sci5, Esperanto, Intel, Samsung, and many others. There is 2 generations of cores. SVERV EH1 is our first core. It's a 32-bit 9-stage 2-issue core. Then SVERV EH2, which is a dual-threaded version of EH1, upgraded for performance and targeting 16-nanometer TSMC. And then there's a SVERV EL2, which is a small 4-stage core, single-issue, also targeting 16-nanometer TSMC, which targets small FSMs in storage controllers. The Western Digital partnered with CODASIP, which is another CHIPS Alliance member, and CODASIP is currently providing design verification and integration services for SVERV EH1 commercially. So the core is actually an open source, but CODASIP will work with customers and help them with integration and verification. So this is the SVERV EH1 core architecture. This is a 9-stage pipeline, and it implements RISC-V 32-bit architecture, including integer, multiply, and compression. Compression is important for code density. And it has only 3 stall points. So we keep pipeline busy with minimum stalling. Stalling points are only on the fetch, align, and decode. It's super scalar. It has a dual issue pipeline. And this is very important because you can get approximately double amount of work done by having 2 execution pipelines. And more importantly, inside each of the pipes, there are dual execution engines. So if you look carefully in this pipe, when we get an instruction that comes after the load, which is very common, you load a register, now I want to do some addition. The data loaded in the register may not be available immediately due to the memory latency. So we have a second opportunity. We go through the pipeline, and then 2 clock cycles later, there is a second execution unit after the register actually has been successfully loaded. So this gives another performance boost. And overall core mark per megahertz for this core is approximately 5. And for those of you who are maybe not familiar with this benchmark, we provided this data comparing some of the popular industry cores, core mark scores. Obviously, Intel out-of-order processors will be very high on these scores. These are renormalized for a single thread, and then renormalized to frequency, right? So if you look at aggregate core mark scores, then the big chips from Intel and AMD will have very high aggregate results, but this is renormalized for a single thread. So what's important here is that this type of a core gives about 50% boost on average compared to the single issue cores, such as RISC-V cores that came from academic community. This is obviously important. If you're accelerating legacy code, you want to get that boost. For those of you who are interested to learn more details, just go to the github.com Chips Alliance and download the source code. Firmware and software toolchain support is of utmost importance. Western Digital has open sourced a lot of RISC-V toolchain and infrastructure. RISC-V supports two main open source toolchains, GNU, which is a GCC compiler, and LLVM. GCC stable upstream versions now include working 32 and 64-bit RISC-V support. And LLVM 9 supports RISC-V, it's upstream recently. On code density issues, we have launched a new workgroup inside RISC-V. Western Digital is vice chairing this group. And a lot of effort has been put into this, and I can say in the last 12 months, significant effort in community has been done, and RISC-V code density is now in parity with other commercial cores. You can basically say within 5%, and in some cases actually better. We worked hard on this, and for example, in Western Digital, we presented this on GNU Cauldron last year. We did a common load store patch for GCC where we took the advantage of compressed instructions. It's important to provide the software for embedded and IoT applications. Western Digital has launched a new COM-RV overlay workgroup inside RISC-V. We are chairing it. It's basically an old-fashioned technique, very applicable to IoT and embedded, where instead of having a more complex RTOS that takes a lot of space, you use this technique to load real-time, to load code real-time at the moment when it's needed. And it's threaded with a toolchain, and it allows significant savings in SRAM, leading to small footprint, lower power, lower cost, important for IoT. Then we came with the SWIRV EH2 core, offering even more performance, right? So this is the first RISC-V embedded core fully verified that supports 2 threads. We support RISC-V 32-bit integer, multiply, atomic instructions, important for embedded compression, and also the bit manipulation instructions with this funky name ZBB and ZBS. The typical throughput gains will be, depending on the code, between 1.6 to even 2x. We'll show some data on that. Above aligner, which basically figures out compressed instructions in RISC-V and gets them ready for decode. Above aligner, threading is vertical. There's plenty of throughput in the fetch engines. And then in aligner and below, we actually have simultaneous multi-threading. This core supports fast interrupt. We'll talk about it later in hardware. But most importantly, brings a significant performance improvement, right? So in the single-threaded mode, if you run one thread only, now we get about 6 core mark per megahertz. And in a dual-threaded mode, we get 7.8 core mark per megahertz combined. This is like a 3.9 core mark per megahertz per thread. So this is very interesting because it basically, the industry average is around 4. So this core on the area of a single core will give performance of 2 cores and still support very low latency interrupts. The target frequency is 1.2 gigahertz and 60 nanometer in a worst case corner. If you look at in the best cases, the target frequency goes very high up. Multi-threading is a key feature of this embedded core. So instead of two distinct cores, multi-threading allows significant efficiency improvement by running two software threads, we call them hearts in the RISC-V lingo, on the top of already fairly capable superscalar core. And this diagram on the top roughly explains what's happening. You know, if you have use cases like in DataPad firmware, where there's many excursions to the bus that may take multiple clock cycles, or maybe accessing slower memories for controller operations, with a single core, you would have a lot of stalling. With a dual-threaded core, you're running two independent threads, and another thread can take advantage of the first thread stalling and execute at the full speed. Overall, you can, you know, if you have this kind of a use case, overall the CPU utilization can become very high, and in practice, you get two cores for the area and power of one. This is an example of a string compare running from the closed couple memories. You can see if it's being run as a single thread, we are getting about 1.4 IPC executing from instruction cache and data closed couple memory. If we run in a multi-thread mode, so we run two instances of string compare, we are literally getting IPC of 2. Because it's a dual issue pipeline. So this kind of tells you that in some use cases you literally get double performance. Another interesting feature is fast interrupts redirect. So this is a complex topic to explain in 1 or 2 minutes per chart, but for details, please see chapter 761 of the SWIR EH2 core documentation, which is available on the CHIPS Alliance GitHub. RISC-V architecture has so-called vector external interrupts, and when the core takes an external interrupt, it initiates a specific sequence of events that basically require us to save registers that are used in the handler, which is standard, storing to the MICPT control status register, to capture a consistent claim ID, which is standard. Load the MAHAP control status register, load the memory location, and finally jump to the address to start executing the specific interrupt source-specific handler. What we have done in a fast interrupt redirect, we have took this first part of the architecture, including external interrupt vector table, and we put everything in hardware. And hardware gates will actually execute this whole process, capture a claim ID, look through the external interrupt vector table, which is now in a closely coupled SRAM, and with this kind of architecture, we got the ISR latency down to maybe like 3 clock cycles. So if you're executing at 1.2 gigahertz, we are looking at 1 to 2 nanosecond latency in the interrupt. This is implemented only hardware, and it's a build argument for EH2 core. So you may or may not want to use it depending on the use cases. And it supports up to 255 interrupt handlers. Big cores are not all that's important. Small cores, you could argue, are even more important, especially if you're using a large number of them for different hardware acceleration function in the SoC. We have released EL2 core, which is a second generation core, also supports atomic and compression and bit manipulation instructions. It's a simple, highly optimized 4-stage pipe with non-blocking microarchitecture, 0-cycle branch target buffer, and with worst case branch mispredict penalty of only 1 cycle. And basically, it's designed to run very close to 1 IPC on a wide range of workloads. Also supports, as a build option, fast interrupt redirect support. And it has a fully pipelined DMA support. So DMA accesses our pipeline. We get about 3.6 core per megahertz on this core and rising. Actually, more recent measurements are trending toward 4.2. The target frequency is 600 megahertz, and this is for 16 nanometer TSMC worst case core. These are some of the IPC results on this score. As you can see, on a wide range of benchmark, Dry Stone, Cormark, Matrix Multiply, SHA-256, most of the cases IPC is between 0.95 and 1. That's not surprising. That's exactly what we have designed the score for. This is an interesting chart that tells you a little bit about the breadth of the acceleration that you can get with SWIR VH2. On the x-axis, we basically put a IPC for the single-threaded code execution. And on the y-axis, we put a multi-threaded instructions per clock cycle. And you can see for those applications that have relatively low IPC, like 0.4, if you run them on the EH2, you will get roughly double the acceleration, which is exactly what's expected. And then obviously, as you cross, so you get really like nearly ideal acceleration. Obviously, now if you cross into range between 1 and 2, you cannot expect doubling, but it actually stays for a wide range of workloads. You are getting as you can see between 1.6 and 2 average speedup. And that's pretty awesome. And I think we see in storage applications closer to 1.9. We have described a range of SWIR RISC-V customized scores. They are finding new applications in flash controllers like main CPU, like datapad CPU, like finite state machines, sequencers for individual NAND channels, power management, and root of trust. And I should point out that open source root of trust project called OpenTitan is also using RISC-V core called IBEX. So to conclude, we described use cases for embedded and storage controller applications. They have very high requirements on reliability, performance, power, and security. And we have delivered 2 generations of SWIR embedded cores, EH1, EH2, and EL2, that meet or exceed demands of most embedded designs for storage controllers. And I would say especially in performance, power, and a ratio of performance to power significantly exceed the cores from other architectures. We have demonstrated very high benchmarks and actual usage performance improvements through superscalar architecture and through multi-threaded designs. And it's important to emphasize that this is the first multi-threaded, fully verified RISC-V cores for embedded use cases because it does support ultra-low interrupt latency through hardware optimizations. And for small cores, which are important for hardware accelerators in larger SoC systems, we have demonstrated high IPC and very low power in practical use cases. If you want to learn more about open source RISC-V core, visit CHIPS Alliance or join CHIPS Alliance and participate in the revolution of open source high performance embedded RISC-V cores. Thank you very much for listening, and it was a pleasure to present at Flash Memory Summit. Please don't hesitate to ask any questions either to the FMS application, or feel free to send me an email directly on zvonimir.bandik@wdc.com. Thank you very much.